Now someone can start.
Yeah. So, good afternoon, everyone. Welcome you all to the second talk of our mini series on Lie Algebras. So, all of us, as we know, the spokesperson for today's talk and all the talks here is Professor Ilangovan, sir. So, welcome to you, sir. We also have a special guest among us today. That's Subramanian, sir. Welcome to you, sir. Welcome to all of the people. So before we move into the talk, I have some basic instructions to everybody here. If you have any kind of doubt, kindly put it in the chat box or use the raise hand feature of the Zoom. Uh, at the end, when you are supposed to ask questions to sir, you can again use the chat box or you can use the raise hand option. For those who are live on YouTube, you can text any questions in the chat box. We'll make sure that these questions will reach the speaker. Over to you, sir.
Thank you. Since we are a little bit delayed already, I have written something on the board. Is the board in focus now? Yeah. Let V be a finite dimensional vector space of dimension n. GLV is the set of all linear transformation from V to V. Then from simple linear algebra, what I would call as fundamental theorem of linear algebra. We know that GLV can be identified naturally with GLN because I will keep mixing these things very happily without any bother. GLN is GLV and GLV is GLN for me. Okay, so we have defined Lie algebra homomorphisms. And the representation of Lie algebra. And as I said yesterday, interestingly, the properties of Lie algebra make sure that we get a representation automatically So this is the nice thing about Lie algebras. If you want to understand Lie algebras, we can just take this particular representation. This is what we are going to be using quite a lot. And this is called adjoint representation. Denoted by add. This is going to go from L to GL. So L is our Lie algebra. And the interesting thing is it has a representation in GLL itself. We don't have to look for anything bigger. Add is going from L to GLL. What's the definition? For every xy in L, add x of y is going to be x bracket y. So add x is supposed to be a linear transformation from L to L, and it should satisfy various conditions. So first let us verify all those conditions. First of all, add x should be an element of GLL, that is a linear transformation. This is where the bilinearity is going to come into picture. For any two scalars C1, C2 in C, Y1, Y2 in L. What does this mean? We have to check add x of C1, Y1 plus C2, Y2. What this is going to be? This should be C1 times add x y1 plus C2 times add x y2. That is when it is a linear transformation. By definition, this is x comma C1 y1 plus C2 y2. This is the definition of add x. Add x of y is x bracket y. So x comma c1 and y1 plus c2 y2. By linearity of the bracket, we know that this is nothing but c1 y1 plus c2 x. We have fixed x here, and the second variable only we are changing. Bilinearity precisely means that we fix one variable and in the other variable it is linear. And this is nothing but c1 add x of y1 plus c2 add x of y2. Okay, so bilinear condition helps us to say that add x belongs to GLL. So this is the first condition. For every x, add x has to be an element of GLL. And for a representation, two other conditions we have to verify. It should be a linear transformation from add. Second is this, add from L to GLL is a linear transformation. So for this, now we have to take elements here for every, let's say, d1, d2 in C, x1, x2 in L, add of d1, x1 plus actually y also d2, x2. So we have to check what happens to add of d1, x1 plus d2, x2. It should be d1 add x1 plus d2 add x2. This is a map from L to L. So we have to verify it on y. By definition, this is d1 x1 plus d2 x2 comma y. Again, bilinearity is what is going to help us. We know that once you fix the second variable y, first variable we have linearity. So this turns out to be d1 x1 y plus d2 x2 y. And this is precisely d1 add x1 of y plus d2 add x2 of y, d1 add x1 plus d2 add x2. So for every y, add of d1 x1 plus d2 x2 turns out to be d1 add x1 plus d2 add x2. And it's a linear. So add is a representation is what we are trying to prove. First, it has to be a linear transformation between two vector spaces. And then the last one, it has to satisfy the property of a Lie algebra homomorphism. So Lie algebra homomorphism means add x, add y, Lie bracket should be equal to add xy. This is what we have to show. For every xy in L, add x, add y bracket should be add xy. And again, these are linear transformations from L to L. So we have to evaluate at some point. So for every z, L, add x, add y of z. So this we have to verify and conclude that it is coming from the right hand side. Add x, add y of z. See, L is arbitrary algebra. We don't know what the bracket is looking like. But GLL, we know what the bracket is. It is precisely add x, add y, minus add y, add x. So here we know what it is. This is add x, add y of z, minus add y, add x. In GLL, this is the bracket. So what does this turn out to be? By definition, this is add x of yz minus add y of xz. Add x of z is Lie bracket xz. Add y of z is Lie bracket yz. Now further, when we take add, we get x yz minus y. So add x, add y minus add y, add x of z turns out to be this. And first one order is nice, x, y, z. Second one somehow there's a slight change. So let us rectify it by taking this. This is where the anti-commutativity comes. By anti-commutativity, minus xz is same as zx. So what we get is xyz plus yzx. Now it seems to be the proper order. And the last one, that which we have not used, namely the Jacobi identity, that is what is needed here. What do we know? Xyz plus yzx is nothing but minus zxy. By Jacobi identity, we know that. So all three properties are used here. Now again minus I can interchange and get this. By anti-commutativity, minus zxy is same as xyz, and this is what is add xy. So we wanted to show this equality here, add x, add y equal to add xy. So for every z in L, this satisfies. Hence, add x, add y, add xy. Hence, now everything is done. Add from L to GLL. It's a Lie algebra homomorphism. So this is the very, very nice property about Lie algebras. Whatever abstract Lie algebra you take, we have this adjoint representation, L to GLL itself. We have a nice Lie algebra homomorphism. Though L may be abstract Lie algebra, we don't know anything about the Lie bracket. In GLL, we know the Lie bracket is exactly like GLN, xy minus yz, and that is why it satisfies. And all the three properties are fully used. So we have a Lie algebra homomorphism going from AddL to GLL. This is something very, very important, and we will be using it extensively in what we are going to follow up. So now we return to general Lie algebra homomorphism. Let L1 and L2 be arbitrary Lie algebras. We have defined the Lie algebra homomorphism, L1 to L2. It naturally gives two subalgebras. If you take image, these are all easy verification that image T contained in L2 is going to be a Lie subalgebra of L2. And then we have kernel T. This is a Lie subalgebra of L1. Okay, these are all routine checking. You people might have done it in group homomorphism, ring homomorphism, vector space. So same kind of thing works. And as always, kernel has a little bit extra property. What is the property of kernel T? We take any element in kernel T and any element in L1. So I take any element in kernel T and any element in L1. What do we get? T of x bracket y. Since it's a homomorphism, this is Tx Ty. Since T is a Lie algebra homomorphism, T of x bracket y is same as Tx Ty. And what is Tx here? X is in the kernel, so Tx is 0. So we get T of xy equal to 0 comma Ty. This can be verified to be 0. So whatever y you take in L and x in kernel, the Lie bracket xy again is in the kernel. So this is the extra property of the kernel. Image doesn't have such luxury, but xy belongs to kernel T, whatever x may be in kernel and y is in. And this is what leads to the definition of an ideal This leads to the definition of ideal. I is an ideal of L if, first of all, it should be a subalgebra, and then for every x in I, y in L, the Lie bracket xy should be. And of course, the easy trivial examples. These are the trivial examples of L. 0 and L are always ideals of L. And of course, we are writing for a general Lie algebra. So again, a general example, take the center. This is the definition of center. Set of all x in L such that Lie bracket xy is 0 for every y in L. And this also is a ideal. And one more example. Any two elements in L you take x and y, take the Lie bracket xy. Just taking Lie bracket won't help because it may not be a subspace. That's why we have to take the linear combination of all the elements. We take linear combination of all the elements, then we get a derived algebra, and one can check that this is also an ideal. And when you talk about center, one can make a simple remark that what is the kernel of add? By definition, this is all the elements such that add x is 0. That means all the elements such that add x of y is 0 for every y in L. This is same as set of all x in L such that xy equal to 0 for every y in L. So I'm just remarking what is kernel of the adjoint representation we talked about. Kernel of add is set of all x in L such that add x is 0. Add x is 0 means it's a linear transformation, so it should be 0 at every y. That precisely means this, and this is nothing but center of. So yesterday at the end I mentioned that every Lie algebra is a subalgebra of GLN. That means it's a linear subalgebra. So if center is 0, center is 0, automatically L becomes a linear Lie algebra because it is going to be a subalgebra of GLN. Okay. We got to this definition of an ideal by seeing the property of the kernel, and this is another remark I can make. I will require a proof, but nevertheless we can just make it a remark. Any ideal I of L is kernel T converse also is true. Any ideal can be obtained as kernel of T, some kernel. What is that K? You know that K has to be this quotient. We know that quotient of vector space by a subspace, but here we have a Lie bracket, so we have to check a Lie bracket. Because of the definition of ideal given here, it will be worked out that L mod I is again a Lie algebra, and this T is a homomorphism. T is natural homomorphism, and kernel, of course, as you can see, is I. So I will leave it as an exercise. We are not going to need it much. So now comes the important definition, the target of this series of talks. So We have already seen, of course, the trivial case 0 and L are the ideals. It must happen that these are the only ideals. Then we call it simple. The first condition that put LL is non-zero. See, if LL is 0, what happens? L becomes abelian. And when L is abelian, if it has no proper ideal, that means it is one-dimensional only. Even if it is two-dimensional, we will have a one-dimensional sitting there. So we are just avoiding this. This condition is put so that this one-dimensional Lie algebra is avoided in this case. That's all. And the example for this. I've been telling you SL2 is so important, and yesterday we have done enough calculation with SL2. So this is the claim. This is the definition of simple Lie algebra, and the first example, the smallest example in some sense, is SL2. The claim is that simple Lie algebra. Recall these things. H equal to 1, 0, 0, minus 1, x equal to 0, 1, 0, 0, y equal to 0, 0, 1, 0. And we had done this D brackets, hx equal to 2x, hy equal to minus 2y, xy equal to. Okay, all these calculations we have done yesterday, that is what is going to be used in proving that SL2 is a simple Lie algebra. What is the definition? 0 and L are the only ideals of L. So if I take a non-zero ideal, it should become whole of L. Let I not equal to 0 be an ideal of SL2 to prove that I equal to S. Right? We are trying to prove that SL2 is simple. SL2 is simple means, of course, we know that it is not abelian. We are not in random characteristics, so you can see that it is not abelian. First condition is fine. 0 and L should be the only ideals. So if I take a non-zero ideal, automatically it should be whole of SL2. This is what we have to verify, and this is where all these three properties are going to use. We have checked those conditions earlier. That is what we are going to use. So let us take some non-zero element here. Let ax plus bh plus cy be a non-zero element in I. We are assuming that I is a non-zero ideal of SL2. So we take arbitrary element, non-zero element in I, ax plus bh plus cy. By definition of ideal, x comma ax plus bh plus cy belong to I. By definition of ideal, if I take Lie bracket with any element of the Lie algebra, it should belong to the ideal. I take x in particular, x ax plus bh plus cy should be equal, belong to identity. And by these calculations, you know that xx is 0. What we get? 0 plus bxh plus cxy. This is what we get. And what is xh? Here we have written hx. Hx is 2x. And we know that Lie bracket is anti-commutative. So what we get is minus 2bx plus ch. Okay, we have just taken Lie bracket with respect to x, and what we have got is that minus 2bx plus ch belongs to I. we again take the bracket with x. By the same reasoning that I is an ideal, when you take bracket again, this should become there. Xx is 0, and what we are left with is this. So twice we have applied x, and we managed to get rid of the coefficients a and b, and we have got minus 2cx belongs to I. So first case, c not equal to 0. Suppose c is not equal to 0, what does this mean? Minus 2cx belongs to I. This means x belongs to I. Okay, since c is non-zero, we can multiply by the 1 by minus 2c and get x belongs to I. And now again I is an ideal, x belongs to I. You can use x bracket y. Y is arbitrary element of SL2 and x belongs to I. So x bracket I belongs to I, that means h belongs to I. And once h is an I, hy belongs to I, that means minus 2y belongs to I. This means y belongs to I. All these things tell you that I is S. This is what we want to prove in general. We have taken an arbitrary non-zero element ax plus bh plus cy, and then by applying x twice, we managed to get rid of a and b. We got cx minus 2cx. If c is not 0, this is the first case. If c is non-zero, we are able to get that I is SL2. Now suppose c is 0. We are going to repeat the same argument only. You can see here, if c is 0, we have minus 2bx belongs to I. This will be the case 2. B is non-zero. That means x belongs to I. That means yh belongs to I. That means I is same as before. Once you get hold of x by the Lie brackets, we can get y and h. So case 2 also we are through. C is not 0, we are through. B is not 0, we are through. What we have left? We have left with b equal to c equal to 0. Ax belongs to I. Since it's a non-zero element, this means there. So again, x, y, h belongs to I. Okay, so we have used all our calculation that yesterday we did. This Lie bracket hx equal to 2x, Lie bracket hy equal to minus 2y, Lie bracket xy equal to h. All that to conclude that SL2 is a simple Lie algebra. Okay, so this is just the beginning of simple Lie algebras. What we have seen is that SL2 is a simple Lie algebra. And interestingly, as I have been telling you so many times, Lie algebra theory is very, very nice. If you understand what is happening in SL2, you can understand the whole of the Lie algebras. Before we attack the general SLN, we need to expand our concept, basically the concept of eigenvalue. . Okay, so before we move on to tackle all SLN, we need some conceptual progress. Suppose we have two linear transformations. V is a vector space, T1 from V to V, T2 from V to V, linear transformation with a common eigenvector. Okay, so we have two linear transformations from V to V with a common eigenvector. So let us say T1V is some lambda 1V, T2V is lambda 2V. We have a common eigenvector for both T1 and T2. What we are going to take is the subspace generated by this T1 and T2. Let us take it as H. Okay, T1 and T2 are two linear transformations from V to V. So they belong to GLV, and we take the subspace spanned by T1 and T2. So suppose P is some element in H. Let us say TB C1 T1 plus C2 T2. Okay, we take some element which is a linear transformation in H. So it's a linear combination of T1 and T2. Let us say it is C1 T1 plus C2 T2. What happens to TV? This is by definition C1 T1V plus C2 T2V. T1V is lambda 1V. This is lambda 2V. So what we get is C1 lambda 1 plus C2. What was the C1 C2? T is C1 T1 plus C1 T2, and TV happens to be C1 T1, C1 lambda 1 plus C2 lambda 2. So the coefficients have come out very nicely like this. If you see what I mean here, from eigenvalues lambda 1 lambda 2, if we have C1 T1 plus C2 T2, we are going to get C1 lambda 1 plus C2 lambda 2. So this is precisely what is called a linear functional. We are getting a linear functional here. What should I call it? Maybe I will just call it as T lambda, or maybe F lambda. We know that every element is a linear combination of T1 and T2. We just define it to be C1 lambda 1 plus C2 lambda 2. And what do we get now? This is what we called as T. So F lambda of T V is what is TV. If you take a T to be C1 lambda 1 plus C1 T1 plus C2 T2, the T action is given by this linear functional. So this is what, when I was talking about expanding the concept of eigenvalue, what we want to talk about is eigenfunctionals. And of course, since I am introducing, I have written just T1, T2. You know that all these things can be taken for any finite dimensional thing. There is no problem at all. Even if we have the same thing will go through for T1, T2, Tn, as long as some n linear transformation has a common eigenvector, we can do this. And this definition, let me not write these things, let me just go to the definition. Okay, so instead of 2, we can do it for any number. And this way, instead of talking about the eigenvalue of a linear transformation, we can talk about eigenfunctional of an eigenvector. Okay, so this is the important generalization we need. This is the okay. If you want to discuss more simple algebras, just one eigenvector, one eigenvalue is not going to be enough. We will be talking about eigenfunctional, and we will try to see what kind of eigenvectors exist for eigenfunctionals. So to see the simple example, we move on to SL3. Of course, going to turn out that in general SLN is going to be simple. We are slowly moving there. First, we have seen SL2 is simple. To proceed further, we needed to expand our idea of eigenfunction, eigenvalue. So that's why instead of eigenvalues, we are moving on to eigenfunctional. And to understand how it is going to be useful, let us just take SL3. So now we are going to have a slightly bigger algebra, but calculations are not going to be that much bigger. If you see what I write, you will know why. What is the dimension of this? 3 by 3 matrices have 9 dimension, 1 less, so there are going to be 8 dimension. There are going to be 8 vectors here. We have H1, X1, Y1, H2, X2, Y2, and then there are these two things, X3 and Y3. Okay, I write down basis, standard enough basis for SL3. I have deliberately written it in this way. You can see what happens here. H1, X1, Y1, if you see, the third row and third column are not at all going to play any role. And H2, X2, Y2, if you see, the first row and first column are not going to be playing any role. I have already mentioned something that in any Lie algebra, we will be looking forward to copies of SL2. And this is what is happening here. At least the first two things are copies of SL2, H1, X1, Y1, SL2, H2, X2, Y2. This is another copy of SL2. Okay, it's very easy to see because of the way it is written. Very, very nice. Since we have done already the SL2 calculation, we don't have to calculate again for H1, X1, Y1 or H2, X2, Y2. But still we have to do some calculation. Let us see what happens to H2, X. Okay, H1, X1, we know it's going to be 2X1 because it's isomorphic to SL2. H2, X1 is what we have to calculate. Let us see what it is. H2, X1 does not follow from any SL2 theory so far. So we are trying to calculate what it is, what happens. Here, only here we have the thing, this thing is 0. I suppose first one, everything is going to be 0. And in the second one, what happens? This with respect to this 0, next one we are going to get a 1. And I suppose we get 0 everywhere. If you do calculation and everything, so many zeros are coming. So what did we get? We get 0, minus 1, 0, 0, 0, 0, 0, 0. And this is precisely minus x. Okay, so H1, X1, Y1 is an SL2. We don't have to do calculation there. H2, X2, Y2, again SL2. We don't have to do calculation there. All I have done is do H2, X1, and I'm getting minus X1. I can tell you without much problem. Similarly, H2, Y1 will be Y. And before coming here, we were discussing how to generalize the concept of eigenvalue and go to eigenfunctional. So if you see here, what have we got? H2, X1 is minus X1. What we have is this H2, X1 is minus X1. H1, X1 I know is 2X. So X1 is a common eigenvector for H1 and H2. So this is the one I was discussing earlier. When we have a common eigenvector for two linear transformations, we can get a linear functional out of it. And this eigenvector corresponds to a linear functional. What is that linear functional now? So this is what alpha 1 is going to do. Alpha 1, H1, H2 is the subspace I am taking. So if you notice, H1, H2 is precisely the ones corresponding to the diagonal matrices. H1, H2 span the diagonal matrices in SL3, the off diagonal ones which are above, that is what we have written now. So what we get, x1 is eigenvector corresponding to alpha 1. This is what we have done. X1 becomes an eigenvector. So we are looking for, suppose I call it as H. Capital H is the subspace generated by all the diagonal matrices, and we are looking for eigenfunctional. This is eigenfunctional. Alpha 1 of H1 is 2, alpha 1 of H2 is -1, and then we can expand it linearly. What we say is that x1 is eigenvector corresponding to alpha 1. So there is nothing special about. You can see that there is a lot of symmetry going on. So similarly, if we define alpha 2 from H, C, alpha 2 of H1 equal to -1, alpha 2 of H2 equal to 2, x2 is eigenvector corresponding. So this is what is going to happen. Similar to alpha 1, we have alpha 2, x2 corresponds to alpha 2. And very, very nice for us. X3 is just going to correspond to alpha 1 plus alpha 2. Of course, it requires calculation. I suppose you cannot do the calculation. It's not very difficult. And similar to whatever was happening in the SL2 case, you remember Hx was 2x, Hy was -2. And we know that here this is an SL2. So H1 y1 is going to be -2y1. I already remarked this. H2 y1 is going to be y. We know that H1 y1 is -2y1. H2 y1 is just y1. So what does y1 correspond to? Y1 corresponds to minus alpha. Similarly, y2 will correspond to minus alpha 2. Y3 will correspond to minus alpha 1. It is so wonderful, so beautiful. All the calculations work out so nicely. If you want to do what we did for SL2, we want to say that SL3 is simple. What we have written down, we took the capital H to be the space generated by the diagonal matrices, and we have written down all these eigenfunctionals, alpha 1, alpha 2, alpha 1 plus alpha 2. It was so nice. Everything worked out nice. Only two things were needed, alpha 1 and alpha 2. X3 corresponds to alpha 1 plus alpha 2. Y1 corresponds to minus alpha 1. Y2 corresponds to minus alpha 2. Y3 corresponds to minus alpha 1 plus. So now it is very, very beautiful. And if you start now, as I said, the proof is going to be very, very similar. There is no change at all. All you have to do is to keep pushing up the way we did last time. When you take I non-zero ideal, there are going to be so many coefficients. So let us see. Maybe I will do easier way out, A2H2 plus a3 x1 plus a4 x2 plus a5 x3 plus a6 y1 plus a6 y2 plus a6 y3. Suppose you take a non-zero element with all these coefficients. What did we do last time? We kept applying x repeatedly, and that is how we showed that SL3 is simple. Here we have two choices or three choices, x1, x2, x3. You can keep applying everything and keep on eliminating variables. So okay. The idea is that these eigenfunctionals are the ones which are going to help us. I am slightly started running out of time. I'll just mention this once. You can see calculation and find out what happens. So this is what is going to happen for SLN in general. You know that similar to this, we can do H1, H2, H3, etc. up to Hn minus 1. For SL2, we had only one. SL3, we had two. In SLN, we will have Hn minus 1. And if you say that this corresponds to alpha 1, this corresponds to alpha 2, this corresponds to alpha 3, etc. Alpha n minus 1. I can just tell you how it goes. This is going to be alpha 1 plus alpha 2. This will be alpha 1 plus alpha 2, alpha 3, etc. Alpha 1 plus alpha n minus 1. This will be alpha 2 plus alpha 3, alpha 2 plus alpha 3 plus alpha 4, etc. Alpha 4. So maybe we will come to this next weekend as well. This is what is going to happen in the general picture, and all these things, transposes will be negatives. Okay, this is the full picture for SLN in general. And of course, when you want to write a proof for this being simple, you may have to use induction as well. But the idea is very, very simple. Whatever we did in SL2, we want to generalize. And what we are going to be useful is called eigenfunctional. That is what we have used to get this. And this is what we get. And generally, this is denoted by AN. AN is what is denoted by SLN plus 1. So this is the standard notation called AN. I urge all of you, there are some BN, CN, DN. These are orthogonal, odd dimension, symplectic, and this is orthogonal, even dimension. So Similar to AN, there are 3 other classes. People can have a look at Humphrey's book they have given, and it so happens that all these are all called classical Lie algebras, and these are all the known simple Lie algebras, AN, BN, CN, DN. There are 4 classes. To understand why these are simple, maybe we have to develop a little bit more theory, which also we will be doing next weekend. But just have a look at all these B and C and D and what it is. I will just mention one joke before leaving. See, before coming to Belur, I was in Hyderabad University, and all of you know that Hyderabad is famous for its biryani. One student joked this. Okay, so one student was joking this, that teachers teach you how to boil basmati rice. And in the exam, they ask you to make Hyderabadi biryani. So essentially, I am leaving with you like that only because SL2, SL3 easy things I have done. This maybe we'll discuss later if needed, but the ideas are all hidden in that only, and B and C and D and naturally are going to be even harder to verify because here this eigenspace decomposition is so beautiful, very, very easy to write. B and C and D are not so nice. Of course, there are patterns, but still one has to do a lot more work. So with that, I stop today. Questions? Yes, Balu, thanks for being there as usual. Yes, students, no questions in this chat box here. Anything from YouTube?
Yeah.
Not yet, sir.
I don't see any questions in the chat box. No.
Yeah. So fine, we meet next Saturday.
Yeah, Bhumika.
Yes, sir. So, as the usual routine of a curry leaf talk, so we'll have a group photo at the end now. So I request everyone to turn their cameras on, and the usual routine. I'll count on till 1, 2, and 3, and at 3 we'll all smile, and there will be a picture taken. So I
Yes,
request
Balu,
everyone
stay
to
this
turn
time.
their cameras. Uh,
Yeah, today I remember it. Yes.
Still somebody has not joined. Dev Jyoti.
okay. Maybe we can take a picture. So, yeah. 1, 2, and 3. Smile, everyone. Yes.
Thank you.
Thank you so much. So now it's time to end the talk. As usual, Sir's talk was really good. And thank you so much, sir, for that. And besides sir, there's another person we need to thank. That is Bikramjit Chaudhary, sir. So he has been really helpful. Whenever the board was unclear, he made sure that everything was intact and it was focused. Thank you so much, sir, for doing it so nicely. Thank you, everyone, for being a part. We'll all meet next Saturday. Thank you. You can, log out.